Dzień dobry Państwu. Good morning, ladies and gentlemen. All of us are aware that more than 70% of our planet is covered with water. We are all interested in what is hidden on the seafloor and what kind of potential resources we can find there, but also what kind of potential danger are hidden in front of us. The problem is that we have some problems how to see the seafloor. We know much more about the surface of Mars and other planets than about the morphology, only morphology of oceanic seafloors. The way to learn about it is to use advanced techniques, in particular geophysical techniques, hydroacoustics, and how to translate this geophysical results into the real data and into the real knowledge about the seafloor and processes ongoing is not always a straightforward task. Today, in the frame of the 5th days of Kiel in Poznań, which are coming from a long tradition of cooperation between Kiel University, one of the leading centers in geoscience, in particular Marine Geoscience worldwide, and our university, we have a pleasure to have a guest in person of Professor Sebastian Krastel, the director of Institute of Geosciences at Kiel University, who is also a head of a group of Marine Geophysics and Hydroacoustics. He is well-known expert on interpretation of high-resolution geophysical data, not only in marine realm but also in lake sediments. His particular interest is mass wasting processes, landslides, and processes which are associated with them. He is quite recognized in the scientific society. For instance, he is a major editor of a recent monograph on submarine mass movements and their consequences. And if you read the list of recent publications of him and his team, only this year you will find a number of papers published in Nature, Science, Geology and other prominent journals. So I hope that all of us will listen today pretty new and very interesting results. Sebastian, the floor is yours.
Thank you, Vitek. Thank you for the very kind introduction. It's my first time in Poznań, and I really enjoyed to be here until now, and I'm pretty optimistic that it will not be my last time. And we will talk about joint projects, and I would be very happy to come back and really work together on a number of projects. And as Vitek mentioned before, there was already ongoing a lot of cooperation between Kiel and Poznań. Title of my talk today is Investigation of Submarine Landslides at Continental Margins, but before I start to talk about that, I would like to take the opportunity to briefly introduce my group, because we're not only working on marine landslides, as mentioned by Vitek. I'm heading a group of Marine Geophysics and Hydroacoustics at the Institute of Geosciences at Kiel University, and I would like briefly to introduce the fields of work and the methods we are using. And Vitek also mentioned that we mainly use geophysical methods, acoustic methods in order to investigate the seafloor. So what we are doing in my group, the methods we use, we are pretty strong in collecting 2D seismic data with streamers and ergans. We have our own equipment in order to do that. We are also able, especially in cooperation with GeoMar, a major marine research institution in Kiel, to collect 3D seismic data, where we then tow a number of streamers behind such a vessel. Not much to see in this figure, but you have some paravanes here, and in between we have a number of streamers. We, of course, collect bathymetric data. Not much is known about the details of the seafloor. Only about 10% of the seafloor are mapped in high resolution. We use side-scan sonar data, an additional method in order to learn more about the seafloor, also about the types of sediments. We use sediment echo sonar data. This allows you to image the upper tens of meters of the sediments at very high resolution. And then based on all of these data, we also take cores in order to investigate material which is really present at the seafloor. These cores, we also have the possibility to measure some physical properties. We have a multi-sensor core logger, which we operate in our institute. And more recently, we also start not to use only acoustic methods, also optical methods, like LiDAR and drones, in order to do some investigations, especially in the coastal zone, monitoring the coastal zone, and so on. And that's all the equipment which is operated by ourselves. and we means that we do data acquisition, we do data processing, and also data interpretation. In order to operate all these systems, especially those here, we need research vessels, we need to go to sea, and we do that on very different platforms. We have the opportunity in Germany to use large research vessels. There's quite a good number of research vessels. It's Research Vessel Meteor, one of the large research vessels. But we also operate in other seas. For example, Peter should know that. That is a little Thai vessel we used a few years ago. And we are quite specialized, and that's indeed different to many other groups, that we can also operate our equipment on very small vessels. So we do something in lakes. That's a boat here, 12 meter long, which we used in Lake Van in Turkey. And if even these boats are not available, we can also go to rubber boats, rowing boats, and collect also reflection seismic data on these boats. And also quite recently, we put all our equipment in a helicopter, flew out to Siberia, and brought our own platform here for doing the research. And on such a little platform and everything fitting into a helicopter, we also collected hydroacoustic data and seismic data. Questions we answer is not only marine mass wasting, more general. I think we investigate sedimentary processes at continental margins. So some questions are listed here. What processes control sediment deposition and redeposition and transport on the shelf? And when, where, and how is sediment transported across the shelf break? And then especially, and that's what we're mainly doing, how is sediment distributed on the continental slope? And there we have a number of processes ongoing. We have gravitational sediment transport, that are landslides, turbidity currents, or channelized sediment transport. And this is further complicated by slope parallel sediment transport due to contour currents. And especially related to the gravitational sediment transport, we investigate geohazards, especially geohazards related to submarine landslides. So we ask the questions, what are the dominant processes and environmental controls of mass wasting? That's a question I will try to answer today. It will be not a full answer, but I will start to answer this question. How dangerous are these landslides, and especially what is the tsunami generation potential of these landslides? We also work in very shallow water. Shallow water, that's mainly related to habitat mapping, where we combine acoustic methods and optic methods, and we do seabed classification, not only using conventional methods, we also try to improve existing methods or develop new methods, and that's mainly for getting thematic maps and for spatial planning. And last but not least, also mentioned by Vitek, we also work quite a bit in lakes, because we have the possibility, the opportunity to get all our equipment to pretty small boats. Here you see bathymetric map of a lake in Macedonia. That's Lake Ohrid in Macedonia. We also have mass basing in these lakes. Here you see major landslide at this part of the lake. And we investigate in principle the sedimentary process acting in these lakes. We looked a bit at the interaction of tectonics and redeposition of sediments. Paleoseismology, I will talk about that in a second, a bit more in detail. And we also recently had a project here in Lake Ohrid in Macedonia where we investigated the interaction of geology and biology, especially evolution and formation of new species. And especially in the lakes, then also in the ocean, we are also heavily involved in drilling in lakes, in the frame of the International Scientific Continental Drilling Program. And we also do quite a bit of work in the Integrated Ocean Discovery Program, which is the ocean drilling program. Here you see the areas where we work. We work more or less everywhere, and so in the entire oceans. We have quite a lot of Northwest Africa, around Europe, but we also work in the Pacific Ocean, Indian Ocean, of New Zealand, and that's more a matter of opportunity. If we have the opportunity to go to specific places, usually people need geophysics to investigate the seafloor, and therefore we are also in the lucky situation that quite a few groups ask us to participate at some surveys. And a major focus of our work in the past was indeed the investigation of submarine landslides, which is the main topic of my talk today. And I structured the talk in that way that I started talking about the relevance, why is it important to investigate submarine landslides, and I will try to answer, and I will not really be able to do that, where, when, and why submarine landslides may occur. And then I will show you two case studies. One is from the Northwest African continental margin, and one is from southern Italy. And what you see here in the background is a submarine landslide. That's the island of Tenerife, one of the Canary Islands. There's a coastline here, and everything you see here, that are landslide deposits, and I will come back to this example later during my talk, only briefly, but I will come back to it. Okay, let's start with the relevance, the significance of mass wasting. Why is it important to investigate submarine landslides? First thing is that they reshape marine landscapes. And Vitek also mentioned that a lot of resources are found at the seafloor, hydrocarbons, other deposits, other hydro resources, and people would like to produce these resources, to get these resources. In order to look at these resources, you should understand how they have been formed, and you need to investigate all processes which shape continental margins, and mass wasting is one of the important processes which is shaping marine landscapes. Then I mentioned that you may use submarine landslides in combination with paleoseismicity or its recorder, potential recorder of paleoseismicity. What you see here is the record of the lake in Switzerland, and these large transparent bodies you have here, that are the landslides in the acoustic data. And especially for these upper two ones, you see there's a red reflector drawn on top. That means that there seems to be at the same similar stratigraphic position. And if you have two landslides occurring at the same time, because they're at the same stratigraphic position, it's very likely to assume that they have a common trigger, and this common trigger is most likely an earthquake. That means if you have a lot of sediments available, and you find a lot of landslides in these lakes, for example, and then you may date these landslides, and if you're lucky, you can use the date of the landslides as recorder for paleoseismicity. And probably most important why people are willing to spend money for this type of research is that they also present a major geological hazard. And the hazards which are associated with landslides, on one hand, is they may destroy offshore infrastructure. I will show a few examples in a second. And they're also capable to create destructive tsunamis. Principle is shown here. If you have a mass which is moved quite down quite suddenly, then you have a deficiency of mass here. Here you add additional mass, the entire water column on top is in motion, and that's always a condition you need to create a tsunami. And people estimate that about 15 to 20% of all tsunamis worldwide may be triggered by submarine landslides. And one last point, and there are very much more points, why it's worth to investigate submarine landslides is also discussed in relation to climate change, warming. You probably all know that we have gas hydrates at continental margins, which host a large amount of gas, methane. And these gas hydrates are only stable under low temperatures and high pressures, and if you get global warming, then these gas hydrates may start to dissociate, and methane is released. And if you add methane to the atmosphere, this may contribute to global warming on one hand. On the other hand, these dissociation of gas hydrates also may trigger landslides, because these gas hydrates are more or less a glue for the continental margins. So if you dissociate gas hydrates, you create a large amount of methane, and then you may destabilize the slope and may create destructive landslides. That these things really happen, that they are really major geological hazard, I want to show you a few examples, and probably the most famous example, maybe most of you have seen it before, is the Storegga landslide of Norway, which is a very large landslide off the coast of Norway, which happened about 8,000 years before present. And here you see the outline of this landslide, and all these submarine landslides, they are much larger than any landslides we know on land, much larger than terrestrial landslides. We'll talk about the sizes in a second. And the age is well known. People started to look for tsunami deposits related to the Storegga landslide, and they found, or they reconstructed tsunami heights of about 10 meters at the Norwegian coast, about 5 meters at the Scottish coast, and here for the Shetland Islands, they were able to reconstruct tsunami heights of more than 20 meters. So really a significant tsunami. And you may imagine if such a tsunami would happen today, that would be a real disaster with a densely populated coast. But luckily, it seems that it's very unlikely that this happens during the time of the present sea level high stand, and I will come back to this point in a second. It's a pretty old example. There are more recent examples, and maybe the most recent example is the Palu tsunami. You heard about that most likely, which happened just a few weeks ago. This tsunami hit the coast quite by surprise, because the earthquake which was related to that was mainly a strike-slip earthquake. There was not much vertical movement, and in order to create tsunamis for earthquakes, you usually need vertical movement. And this movie which is showing this tsunami, which you found on the internet, you see that here, it's a tsunami which is coming here. It's a movie from a fisher boat. And as the height of the tsunami can't be explained only by the earthquake, other reasons have to be considered. Most likely, on one hand, it's the shape of the bay, which had an amplification effect. And in addition, people think nowadays that submarine landslides probably also contributed to the height of the tsunami. And Vitek just told me that he may go to Indonesia later this year in order to do some field surveys, and at some point it would also be very nice to investigate the seafloor in order to see whether there are some young submarine mass-based events which have contributed to the tsunami. Talking about infrastructure, the major problems related to submarine landslides are cable breaks. A very famous example, also quite long ago. There are cable breaks related to the Grand Banks landslide and tsunami, which happened here in Newfoundland of Canada, and this event happened in 1929. And related to this event, there was a major landslide, first an earthquake, then a landslide. This landslide quickly disintegrated into a turbidity current, and this turbidity current most likely damaged a number of cables. There was a temporal sequence of events, so that the velocity of the turbidity current could be reconstructed. And it was first actually proved that these turbidity currents may have underwater. Also nowadays, this is a major problem. There are a lot of cables, for example, of Taiwan, and they are partly laid across channels, and inside these channels we have regular sediment transport, and once in a while these cables get destroyed, and that's quite problematic for the worldwide internet traffic. Another example where offshore infrastructure may be destroyed, have not been destroyed, is coming back to Storiga. Here you see the headwall area of the Storiga landslide, the shelf area about 250 meters deep. Here it's a missing part, which have been mobilized during the Storiga event about 8,000 years before Krasing. And directly beneath the headwall of the Storiga event, there's a very major gas field, the Ormen-Lange gas field. And that's that large that it was very attractive for industry to produce out of this gas field. And it's quite deep. Water depth is about 1,100 meters. That means all the infrastructure for production needs to be built on the seafloor. And before the companies received permission to do that, they had to prove that no landslide will happen in the next 50 years at least. It was the estimated time of operation for such construction. And in a very large joint project involving all Norwegian institutions, universities and so on, it's shown that it's extremely unlikely that something will happen here in the next 50 years, and therefore the companies received permission to build infrastructure on the ground, on the seafloor. But nowadays, if platforms are built or whatever, also the companies, they are really investigating stability in order to make sure that nothing will happen, because on one hand it would be a major loss of money, and on the other hand, if such infrastructure would be destroyed, most likely it would also be very bad for environment if you get all the students like that. So hopefully I convinced you that it's pretty important to investigate submarine landslides. Then next we can try to answer where, when and how do they occur. And the question, where do they occur? Here you see a map which more or less points out the distribution of major landslides worldwide. Major is not a very quantitative term. This is defined by different people in a different way. And for sure, this map is also not complete. It's heavily biased by the availability of data. For example, if you go to passive margin like Northeast Africa, you see a large number of landslides here, red dots indicating large landslides. You don't see anything on the other coast here, on the eastern African coast. And this is most likely caused by the case that not that many data available are for this area. Nevertheless, so this map is for sure not complete. Nevertheless, if you compare areas which are relatively well surveyed, like here the European margin and North African margins, this active margin of South America, which is also relatively well surveyed, you see that these very large landslides mainly occur in passive margins, not in active margins. And the reason for that is most likely that passive margins you have long time for the sediments to build up very thick sedimentary successions and not major earthquakes, which may destabilize these sedimentary successions very quickly. And therefore, generally speaking, you have very large landslides, but infrequent landslides with passive margins, while active margins are characterized by more frequent but smaller landslides. And I can show you a few examples. The first example is north of Spitzbergen, north of Svalbard. Second example is of South America, and then I'll show you another example in order to give you an impression of the size of these landslides from the Gulf of Mexico. We start with this one here, north of Svalbard. That's a very large and very impressive landslide, the so-called Yamak landslide. It's on a passive margin, as mentioned before. The largest known slides occur on passive margins, and here you get an estimate of the volumes of more than 20,000 cubic kilometers, really a lot. Runout distance maybe of more than 800 kilometers. And here this is an impressive example where you see the height of the head wall, which is about 1,400 meters in comparison with the Eiffel Tower. So it's really very high head wall and a very dramatic and very large landslide. If you go to active margins, landslides may look like that. That's an example from off Chile. With the sedimentary ridge here, and on this ridge you have also clear indications for a landslide, missing mass, positive mass, and this landslide, the previous landslide has a volume of 10,000 of cubic kilometers. This landslide only a volume of half a cubic kilometer, which is still large in comparison to most terrestrial landslides. And as mentioned before, generally speaking, active margins are characterized by more frequent, but generally smaller landslides. Which does not mean that no large landslides occur also passive active margins. So we also have some examples for very large landslides and active margins. And one other example where do they occur, I can show you an example from the Gulf of Mexico. This is something like a medium-sized landslide. And we have this escarpment, the 60 escarpment here. And we have some landslide scars like this one here. The escarpment is formed by salt tectonics. We have a lot of sediments available due to the sediment from the Mississippi River. And if you zoom in here, which is not a very large landslide, mainly medium-sized landslide, and zoom in here, this is downtown Houston. To scale, you can see that you can easily place downtown Houston in such a landslide scar of a relatively small landslide, which hopefully gives you some impression about the size these submarine landslides may have. So next question is, why do they occur? And this question is indeed much more difficult to answer. There are a number of reasons, and I won't go through all of them, it would take too long. In principle, if we talk about why landslides may occur, we always have to distinguish between so-called preconditioning factors and the final trigger. And preconditioning factors, that are the factors which build up a potentially unstable slope. That means you only need small forces afterwards in order to destabilize the slope. Some of them are listed here, and most important ones are maybe marked in bold. Of course, you need a sloping terrain. If you don't have a sloping terrain, you don't have the force of gravity, and you won't create a landslide. And one thing which is pretty important, I will come back to this later during my presentation, are weak layers. Weak layers means that there are some layers which are mechanically weak. They may be pretty widespread, I will show you later, and these weak layers, most likely these landslides occur along these weak layers because the shear strength of these weak layers is much smaller than the shear strengths above and below. So that are the potential depths or stratigraphic levels at which a failure may occur. Then high sedimentation rate, if you have a lot of sediments available and there's not enough time for compaction and settling of the sediments, this makes the slope potentially unstable. Unfavorable layering, for example, you have dense material onto less dense material or loose sand under a low permeability layer. This may cause the potentially unstable slope. And then excess pore pressure is also pretty important. If you have excess pore pressure, then you reduce the shear strength again, and this also may build up a potentially unstable slope. And then usually you need a final trigger. These final triggers, there's also a very long list, but I would say at least 90% of all final triggers are earthquakes. So if you have a potentially unstable slope, and then you have maybe even a small earthquake, then forces may be enough in order to trigger your landslide. And the other pretty important thing which is listed here is also again excess pore pressure, which is also closely related to the earthquake. Of course, if you have an earthquake, you have the movement, this mechanical thing which is ongoing. But also during an earthquake, you all probably know that you may get something like liquefaction during an earthquake, and due to the movement and the cyclic loading during an earthquake, you may increase the pore pressure in a very short amount of time significantly, and then this combined effect of the movement of the earthquake and the increase of pore pressure, this very often is a final trigger which causes the landslide really to be mobilized and then to be moved down slope. Actually, about the reasons why landslides, the reasons, preconditioning factors and triggering factors, so the general reasons are very well understood. Then if you go to a specific landslide and ask the people who investigated this landslide what is the specific reason, then it's getting more complicated, and usually the arm waving starts, and people are usually not very much aware what the final trigger and even what the preconditioning factors are. It's known in general, but really to investigate the specific examples is much more complicated. When do they occur? And that's also a pretty complicated question, which is also heavily debated. You see that you have here a sea level curve for the Atlantic Ocean, and all these dots down here that are landslides. And some people postulate that slides may occur at any time, but an increase is observed, increase in frequency is observed during times of sea level rise, what is seen here more or less. So you have the larger rise of sea level, you have the large number of landslides, and no dots actually get the younger parts. This is heavily debated and doubted by a number of people. Also because the reasons behind that are not really clear. I think it's pretty clear for glaciated margins, when you have ice in the glaciers on the margin, on the shelf, because then it happens the following. It's an example from the Norwegian margin, developed for the historical landslide. The different colors you will see here: green material is moraine material, blue material is clay material, deposited in the interglaciers. And what happens usually if you have these glaciated margins that will deposit clays in the interglaciers, and with the glaciers which are coming, you quickly deposit moraine material on top of these clays, water-rich clays actually. Then you have the retreat of the ice. This layering between clays and moraine material on top is potentially unstable. Then with the retreat of the ice, and due to the retreat of the ice, you get some isostatic rebound, you get earthquakes, and this is then the final trigger for these potentially unstable slopes. So that means you have, at the end of the glaciation, when you have the increase of the sea level, you're getting the situation that you have isostatic rebound, and this triggers then finally the landslides, and therefore you have a correlation for glaciated margins. People also postulate a correlation for non-glaciated margins, but that's not that easy to explain, and I will also come back to this point later. Before we come to the case studies, just one last word: how do we investigate submarine landslides? And that's what I mentioned before. We go out to sea with vessels or to lakes and do our acoustic surveys. Based on the acoustic surveys, we take course. Sometimes with not very nice weather conditions, and then on the course we can do physical measurements. Not my group, but you can also measure mechanical parameters, and you can also measure some of these parameters like shear strength or pore pressure in situ by lowering probes to the sea. Okay, with this I come to my case studies, and my first case study is the Northwest African continental margin. That's an area where I have been working for a pretty long time. Northwest Africa is an old passive margin. One special thing about Northwest Africa is that we have a number of volcanic seamounts and also volcanic islands, like the Cape Verdes, the Canary Islands. And we have different types of landslides. We have landslides related to the volcanic islands, like the Canary Islands. These landslides are well known on the flanks of volcanic islands. I'll show you an example in a second. And we also have landslides on the open slope, very large landslides. And the setting for the Northwest African margin is the following: that we have relatively high accumulation rates of sediments, despite the fact that we have the dry Sahara in the hinterland. That means that you almost have no fluvial input, but due to trade winds, which are blowing away from the coast, we have local upwelling and we have high primary productivity, and this causes then relatively high accumulation. First, let's have a look at the landslides on volcanic islands. We will now place ourselves about here. That's Gran Canaria, that's Tenerife, and we place ourselves here, look to Gran Canaria, and then we are coming back to the first figure I showed you before. That's the island of Tenerife, almost 4,000 meters high. Water depth here in the range of 2,500 meters. That's the coastline. And here you see this very irregular seafloor. We call it a hummocky seafloor. And this is caused by landslide. We have a major flank collapse, most likely related to the volcanic construction on Tenerife. That means magma is intruding into the volcanic island, and then at some point these flanks are getting unstable. Then we have a collapse of the flank, leaving this valley behind, Tuima Valley, and all the material which is involved in this landslide, this disintegrates in single blocks, and these blocks are then deposited on the seafloor. I can show you the movie also from the Canary Islands. Tenerife here, Gran Canaria here. We were just here between these islands. Grayish colors that are backscatter data, which tells us something about the sediment type or special grain size or roughness of the seafloor. And then we have the navigation model, that's the coastline. And then we can use the data to fly around. Here you see a slope which is relatively smooth with a number of channels and gullies. Compared to here, that's a place where we have the landslides, the debris avalanche I just showed you, where it's large blocks. And some of these blocks are pretty large, 2 kilometers in diameter, about 200 meters high. And just here, you see it in a second again, you also see a major incision. Most likely this is also related to a landslide, but we don't see any deposits close by, which means that this incision most likely was formed quite some time ago. Gran Canaria is a relatively old island. The main shield phase of Gran Canaria was about 15 million years ago, and most likely this metal incision, which is down here at the moment is not visible, and this was formed during the shield phase, and all the deposits which are related to this collapse are now deeply buried into the sediments. Here again you see that's a landslide. This is an area not really affected by a landslide, and these volcanic landslides is heavily debated. They have tsunami-genic potential, and it's heavily debated how high these tsunamis may get, which are related to this type of landslides. We did similar things for the entire Canary Islands. We used the distribution of major landslides for the Canary Islands. We have major debris avalanches on all flanks of the Canary Islands. In the western part, we have the younger islands, as known as hotspot trace, and most slides, younger slides, occur on the western islands, because there we have the main magnetic activity, and this magnetic activity seems to be balanced by destruction in the form of landslides. We also have some giant landslides on the old but still active eastern islands, and the long history of volcanic activity seems to be balanced by landslide activity. And luckily, if we talk about not hazards but risk, also has a temporary component. These landslides don't happen very frequently. There's only one giant slide every 150,000 kilometers, 150,000 meters. So leaving the Canary Islands behind, moving on to the open slope, where we also have a large number of landslides, as explained before, relatively high accumulation rate. And we work in this area quite often, and we just published a new compilation of these landslides of Northwest Africa. You see a map from Northwest Africa from South Senegal up to Morocco. And all these brownish colors here, that are major landslides which we identified off Northwest Africa. And if we have a look at this map, then to summarize some general observations, it seems that we have several very large landslides on the open slope and on the places of Canary Islands, as shown here. And an important observation is that we almost have no small landslides. And we don't think that this is biased by data availability. We don't have a complete map, not complete coverage of this entire area, but we have quite a few ship tracks, and we found these very large landslides and transits in between, and also in other areas. We don't have any limitations for smaller landslides. It means that it seems that we really have, if we have a landslide of Northwest Africa, usually it's also pretty large landslides. And then we have some major canyons and gullies, that are these yellow lines here, especially in areas without major landslides. And I can't guide you through all of these landslides, it would take too much time. Therefore, I picked out 2 examples, and one example is the Sahara slide, a very large landslide with runoff distance of about 800 to 900 kilometers here, from here to here. The second example will be the Agadir slide. It's an area where we were quite recently. But let's first have a look at the Sahara slide. That's a bathymetric map of the headwall area of this landslide. We have 2 headwall areas. We have something which we call the upper headwall area here. And we have also the lower headwall area, which is not well mapped yet here, just have one track. The height of the lower headwall area is about 100 meters, and in spring we will have the possibility to go back to the Sahara slide and do some more additional mapping here in this area in order to get a complete map of the headwall area of the Sahara slide. If you look at the upper headwall area, you see that's quite complex, which is quite common for major landslides at continental margins. It does not seem to be a simple headwall, just one major failure. It seems that there are different phases of failures, different generation of scarps, and that's really very typical for all of these major landslides, that they don't occur in a single event. Almost all of these major landslides are multiple events, and these multiple events, it's pretty important to consider, because it's a big difference if you again consider the tsunami generation potential, if all the mass is going down at one step, or whether you have multiple phases, the volumes of the individual failures is much smaller than the total volume, which is usually relatively easy to assess. when we think how these landslides may have happened or what is the type of dynamics of these landslides, for that we collected a number of profiles. First I want to show you one sediment echo sounder profile, which is running parallel to the main head wall here. Then what you see here, these steps, actually it's a scale to a travel time from here to here, that's about 75 meters. Lateral scale is here. And you see that you have very well stratified sediments, and on top you have relatively thin landslide deposits. And the base of the landslide is marked by this yellow dashed line. And the deposits are not that thick in this area because the landslide had been major erosional here in this part, and major deposition starts further down. And what you see here, that the base of the landslide is really characterized by very continuous and pretty strong reflectors. And you don't see any erosion into these reflectors. And this means that we have a bedding parallel translation is sliding along the discrete reflector, along the stratigraphic level, and this implies indeed the presence of discrete weak layers, which must be very widespread, because we see that these failures occur in different levels. So we have more than one weak layer with 3 glide planes, one here, one here, one here. But along these glide planes, we have very continuous reflectors, and this is really a very strong indication that we have weak layers and that these landslides occur as translation slides along these weak layers. That's not the only type of mass movement we have here in the Sahara slide. If you go to the edges, and here this plot shows the side-scan sonar image we have. Side-scan sonar image, you can think about the side-scan sonar image like an illuminated landscape with shadows and bright zones. And if you look here, then you see that with elongated features, there's here the head wall, maybe going in this direction, and it seems, if you do the interpretation here, that there's some large-scale ridges, there's some small-scale ridges. In principle, you have a number of repetitive ridges and troughs, which are orientated parallel to the scarps and perpendicular to the direction of mass movement. And this is usually interpreted as spreading. Spreading means that you most likely had first, this is mainly happening occurring here at the sides of the landslide, the first of the major landslide, evacuating this area, and then due to the missing support of the sediments are not there any longer, due to the missing support and the force of gravity, you start to get spreading. That means a slow movement downslope, which is then resulting in these repetitive ridges and troughs, which are orientated parallel to the scarps and perpendicular to the direction of mass movement. When you think about the age of such landslides, dating of landslides is not always easy. We also took the core here more or less directly beneath the head wall. And before we did this investigation, it was assumed that the age of this failure was about 60 kilo years. This was mainly based on work which was done around the year 2000, where people looked at the deposits, very distal deposits, and they dated these distal deposits 60 kilo years. We did some additional work in the head wall area, took some cores, and that's the gravity core, one of the gravity cores we took in this area. And you see this looks quite chaotic, so very typical for landslide deposits. That's the top of the core, that's the first section, that's the bottom of the core. All this is landslide material. And you may see that there's a little brownish something here on top of this core. That is the typical Holocene sediments you may find off Northwest Africa. And we managed to date actually the sediments immediately on top of this landslide. There was not that much material, and it turned out that this upper head wall area was late Holocene in age, only about 2 kilo years before present, so not that long time ago. And we think that it's one of the largest failures which occurred more in the recent past. And this also shows if you want to investigate such a landslide, it's not enough just to go to one part of this landslide, not investigating just the distal deposits. And you came up with an age. Here we have clear indications that we have another age. And most likely this 2 kilo year event generated this upper head wall, and the 60 kilo year event is related to the lower head wall. But that's one of the reasons we wanted to go back and learn more about this lower head. The second example of Northwest Africa, if we move further to the north, Morocco, that's Agadir Canyon region. Agadir Canyon is a very large canyon here on the continental margin. It's one of the largest canyons in the world. And it's contributing a lot of sediments to the Moroccan turbidite system. And this Moroccan turbidite system is a system of 3 linked basins, the Sena Abyssal Plain, Agadir Basin, and then further out here with the Madeira Abyssal Plain. There is a large number of turbidites, and it's pretty clear that the turbidites must come from the continental margin. And it's assumed that Agadir Canyon is one of the major supply passes for the turbidity currents, which are then finally deposited in the implicit plates in the Northern Turbidite system. The sources of the turbidites is largely unknown, and that's the reason why we had to choose here in this area, and then more or less just by accident we also discovered a pretty marked landslide, the Agadir slide, and the Agadir slide transport originates about 200 kilometers south of the major canyon, and it transports a large amount of material into the canyon. Look at the symmetry, it looks like that. Here we have the canyon, north is down here. That's the headward of the landslide. And you may see here that's undisturbed area. You may see that the uppermost edge of the landslide. The material which originated from here moves down and is finally entering the canyon. And right here we have behind that when this material is entering the canyon, with a significant increase in slope gradient, most likely the landslide will pick up some speed, and this may cause a transformation of a more dendrite-like landslide to a turbidity current. Without focusing too much on this area, I want to focus on the headward area again. We zoom in here to the headward area, and we have a gravimetric map of the headward area. Here you see the landslide scar, missing mass, height of the headwall is about 100 meters, that means 100 meters of sediment have to be moved away, and we also have pretty pronounced sediment waves here in this area which somehow interact with the landslide. You now look at the seismic profile which is crossing here the landslide scar. You see that's the uppermost top of the landslide scar most likely, crossing it in a quite oblique way, and it looks like that. And if you haven't seen the bathymetry before, it's really difficult to see that you have any landslide deposits here. Everything looks really undisturbed, and it looks like normal sediment waves. If you do some careful analysis and trace some reflectors, then it looks like that. If you trace a reflector here, then you come up here and you see that we have much more material on top of this reflector here compared to here. That means that's the area where you cross the landslide scar obliquely, and this sedimentary section is moved away. And it seems to be purely erosive, almost no deposition. Maybe there's a little bit of deposition here. You see more or less chaotic deposit here, but almost everything is moved away. What is pretty interesting, I think, imagine that you have a major landslide, 100 meters of material, 100 meter thick succession have been moved away, and the underlying morphology, these sediment waves, are totally intact afterwards. They have not been destroyed by this landslide. And again, the only possibility to explain that is that you have really a translational slide, which is which developed along a weak layer, a very pronounced weak layer. That means all this material has been moved away, and the material beneath is totally untouched and intact. So again, we have very clear indications that we have a failure along a pronounced weak layer. And that's very common for all the landslides we have off Northwest Africa. Before we evaluate that a bit closer, I also would like to take about timing. This landslide is pretty much older than the Sahara slide. The age of this landslide is about 140 kilo years. We did a population of all the ages we have, dated landslides off Northwest Africa. There are these grayish lines here. This is the sea level here, the sea level curve. And then if you look at that, there's no obvious correlation, at least for Northwest Africa. We don't think that we have a correlation between sea level and the occurrence of landslides. And therefore we don't agree with some of these papers which have written before that there seems to be a correlation. So if we summarize our basic observations for Northwest Africa, then we can say that the Northwest African continental margin is characterized by large, more than 100 cubic kilometers volume landslides, but very infrequent events. They are not irregular. All landslides occurred as multiple failures, most likely in a retrogressive pattern, starting downslope and moving upslope. And the most obvious similarity between all these landslides is that they seem to be occurring along very widespread light planes, parallel to stratigraphy, pointing to the occurrence of very pronounced weak layers, which are very continuous. Timing of failures does not correlate with sea level. And this investigation of these potential weak layers is not that easy, because usually if you want to sample them, if you go to the landslide area itself, then most likely it's not there any longer, because it was the weakest part of the slope, and of course it's gone with the landslide. And that means that you have to go to these places here, and in order to get to the weak layer at these places, you have to drill quite deep. 100 meters, which is not possible with conventional coring techniques. And therefore, we don't have many samples of these weak layers. But luckily, just by accident, we realized that there is an old ODP site, ocean drilling site, that is smaller landslide off Northwest Africa, that's site 6.8, which have been drilled more than 20 years ago. And just by accident, it was a site that was drilled for paleoclimate, so they did not intend to drill any landslide deposits, for sure not. But they realized that there's a major hiatus in this site, and if you look at this profile, that's the location of the site, and you see that you have a landslide here, you have a landslide star here, another one here. That means you can easily explain why something is missing here, because that would be a much better location here to drill. And then you have a landslide which cuts deeper to stratigraphy, but luckily this landslide only affected this part of the slope and not this part of the slope. So here at this location, we were able actually to trace the base of the landslide to the area where the landslide did not happen, and therefore we still have the rich material of the weak layer. And the outcome of this is actually, when we think about weak layers of Northwest Africa, we were able to trace the failure surfaces into the undisturbed sedimentary sequence, and it came out that it coincides more or less with thin, relatively thin, less than 10 meters, diatom ooze layers, which are kept by clays. And diatom oozes, they're very well known for building up excess pore pressure. They're susceptible to building up excess pore pressure during burial, because due to the high compressibility and high water content. And then if you have clay on top, water can't escape, you create overpressure, and therefore most likely you think actually that these diatom oozes make up the weak layers. This means actually, if we continue to think about relation between landslides and climate, changes in global climate of course affect the evidence of diatoms, yeah? And thus somehow the formation of this weak layer is related to climate. That means the preconditioning factors somehow controlled by climate for this example, but not the actual timing of the landslide. The weak layer may be built at a time where we have very good conditions for diatoms to grow, and then they're buried afterwards, and at some time when we have enough sediments on top, everything is getting unstable, and then it gets a mess. And this is now only proven, we only did that actually for one thing, and Vitek also told me that we did something off Japan in a very similar way, and actually we would like to go back to this area and test at least one other example, and I come back to this at the very end of my talk. I want to show you one additional example that is about submarine hazards of southern Italy. That means a different setting, because we have an active margin, and we also had a number of cruises to this area, very nice area for surveying. This is Mount Etna in the background, and it's really very nice scenery. We were even lucky enough to do our survey during the eruption of Mount Etna. We saw lava fountains and lava flowing down the mountain. It was very nice. And the reason that we went to southern Italy is that the continental margin of southern Italy is located along convergent plate boundaries, which are shown here. In most of the coastal areas, they experienced major earthquakes, landslides, tsunamis, historical or and modern times. And one of the most prominent example was in 1908. There was a very large earthquake and tsunami in the Messina Strait, which caused about 80,000 fatalities. So it's really a very major event in the younger class. And the reason for our investigations here were twofold. We wanted to investigate the fault pattern in the Messina Strait. I won't talk about this today. And then we wanted to look for deformation structures of the continental margin east of Mount Etna, which is related to slope stability. And the reason for doing that is more or less explained by Mount Etna. If you look here on land, it's a figure, that's the summit of Mount Etna. And then you have all these colors here, and these colors indicate, well, this is well known, that the entire eastern flank of Mount Etna is slowly moving to the sea. And the speed of movement, more or less here, is in the range of a few centimeters per year. This is actually well documented also on land. You have roads here where you see some cuts in the road, and also if you look at a lot of buildings, you see that there is a lot of destruction on the of these buildings due to the slow movement of Mount Etna in the direction to the sea. And the most common explanation actually for this is that you most likely have here a summit. It's an active volcano. You are getting inflation of magma, intrusion of magma. And this intrusion of magma is causing a bulge of the flank, and therefore the flank is slowly moving, following gravity into the direction of the sea. But all this consideration is not taking into account the submarine part, because since pretty recently, almost nothing was known about the submarine part here, about the continental margin, which is continuing further down. And Italian colleagues and also ourselves, we did quite a bit of work in this area. First of all, here you see the Mount Etna, and that's now the submarine topology, where you see the large number of canyons and channels. You see that we have a major amphitheater here, most likely also the remnant of a major landslide. And there are a lot of interesting features in here, and I don't have time to talk about all of them. And I just want to focus on a very small feature which is here. Here you see that we have some type of lineament at the seafloor. It's also visible in morphology. And interestingly, if you look at the location of this lineament, that's again Mount Etna here, and this part, this color part, is the moving flank on land. Here's the coastline, that's the moving part on land. And the lineament is really just the continuation, the submarine continuation of the moving flank on land. Here on the northern edge, it's we have the Costa Ridge. This seems to be continuation on the northern side, and here on the southern side of Catania Canyon. And just north of Catania Canyon, we have this lineament, which is visible here. And in order to check whether really movements continues at the continental margin, we managed to deploy a geodetic network on the seafloor. Marine geodesy is a pretty new field in marine sciences, because it's not that easy as on land. You can't use any optical methods. Again, you have to use acoustic waves. And the idea about doing marine geodesy is again a network operated by Dioma. We are from the Kiel University, and we don't have the money to operate these large systems. And we have a number of systems, instruments at the seafloor, and they are doing very regular rangings between, they're measuring the distance between these different instruments in every direction. And then if you have a fault in between here, you have a strike-slip movement, then the distance between instruments will change. And that's what we did down here. It's not really done that often before. And here you see the outline of our survey, and this was the estimated fault here, or the estimated lineament. And then we had some instruments on one side and some instruments on the other side. And then this system was deployed for 2 years, and when we started to measure whether any movements are taking place. And interestingly, actually, that's an example of the data set. And here you see the distance between the instrument 2 and the instrument 4. The black dots are the single measurement, and then the red line is the 10-day moving average. You see that for some time not much was happening, and then you have something like here. And that's a movement of about 4 centimeters over a period of 8 days. So it's something like a slow slip event, where you have a movement over quite some days, and it's 4 centimeters. That this is a real signal and not something caused by noise or whatever. You can see here, if you compare instruments 2 and 5, distance, same time, nothing happens. So principal ranging is working, and it seems that we really have a major movement of the flank here at this time in May 2017. And these instruments are also measuring vertical displacement by pressure sensors. It's a bit more complicated because we have the sea level and other effects. But nevertheless, we also see that we have a major drop here, about 1 centimeter, and this corresponds exactly to this event. So this means, to summarize all that, here you see the different instruments, and you see the relatively changes in distances. Blue means that there's a reduction of distance. Red means we have an increase in distance, and this seems to be pretty consistent. And if you summarize the data, then the data we measured is consistent with the dextral strike-slip motion. This is May 2017 event. It was more than 4 centimeters in 8 days. And in addition, we had 1 centimeter of subsidence with the unstable sector relative to the stable sector. Consider this sector as unstable. If you compare this with land data, which have been recorded at the same time, and by GPS and INSA data, then if you measure a profile here, that's the location of the network. You see the lineament again. If you measure the movement across this fault here on land, then you have a displacement same time of about 2 centimeters. If you go to the northern edge, you have a displacement of 1.73 centimeters. That means the movement here on land seems to be less than the movement here in the submarine environment. The movement was much stronger here. And here it was more than 4 centimeters. So, I mentioned before that the most likely explanation for the movement of the flank was magma intrusion here at the summit. But then it's not really easy to explain why you have the largest movement pretty far away from this location where you have the magma intrusion. That means most likely you need to think about other reasons for this moving flame. And summarize that, well, you have the largest displacement increases from the summit to the coast and beyond. And coastal and offshore movements are kinematically consistent. And it seems that we really have that offshore fault accumulates slip of 2 onshore fault systems or even more onshore fault systems. What does it mean? Again, it's very unlikely that the main reason for that is here at the summit. It's not really what we have is that we have the initiation of bale shearing, somewhere seawards, somewhere here. Most likely we have a subsiding continental margin. And this subsiding continental margin is causing a gravitational pull. And the gravitational pull, if you think about hazards, is probably much more dangerous, just the magma inflation here, because not only the volcanic flag is affected by this, the entire coupled system between volcanic flag and continental margin is affected by that. And then, if the entire system, if this continues to go on for a while, then it may happen, and I really want to say it may happen, there's no clear indications that this will happen in the near future, it may happen that this entire area may collapse, and this would be really a major disaster. In addition, actually, this entire movement, inflation and dike intrusions may cause a acceleration of this movement. That's one thing we published quite recently in Science Advances. That was the paper, Gravitational Collapse of Mount Etna Subsistence and Flank. Gravitational collapse just means that the movement is really caused by gravitation, not by magma inflation, and we try to phrase everything really very carefully. Yeah? So we said, we have indications for an unstable flame. We see that the movement is larger onshore, and really this type of measurements on a flame of a volcano has not been done before, geodetic measurements. And that was the main scientific things we wanted to communicate. And of course, we also mentioned, of course, it's a potential danger that this may collapse at some point, but we don't have any indication that this will happen in the near future. And this paper caused really very large media attraction, and then something like that came out here, yeah. Mount Etna warning, British holiday hotspot at risk of tsunami and volcano collapses, yeah. And that's for sure nothing we have said, yeah. It's just a word of caution if you communicate with media, with press. You really have to be very careful what you say and what you would like to communicate, because they will really pick that pieces. Sometimes you don't want to pick them, but they want to pick that pieces which they can sell less. And really, you may read the paper. I mean, we read it afterwards quite carefully, and we realized that maybe some things have to be written in a different way afterwards. It's always easy to realize that, but this is indeed not what we intended to do. Okay, that was the Etna case, and instead of giving a classical conclusion, I would like to spend some thoughts what we may do next, and I just want to say there's plenty of things we may do next. I think one thing which is really important is ocean drilling, is drilling of these landslides would be very useful, because drilling of marsh basement complex would us allow to study the deposits of landslides, the weak layers, because we can drill much deeper than if we drill in the undisturbed sections. We learn more about the frequency of landslides, and we would also be able to install observatories in order to see whether there are any precursors of submarine landslides. And especially for the Northwest African continental margin case, we just submitted an IUDP proposal, which is again mainly focused on paleoclimate, but we also included an aspect of geohazards in this proposal, and we hope that this proposal will be accepted. And then I think also the tsunami generation potential of these landslides, is not really well known. This is super animation. Combined modeling of landslides and tsunami, I think that's really critical in order to get better estimate for the tsunami height. And the most complicated part of that is really the dynamics of the landslide itself. Yeah? Because we don't know whether landslides, we not always know whether landslides are single landslides or multiple phase events. We don't know much about initial acceleration of these landslides, and that are all factors which heavily control the potential tsunami height. That means we need to learn much more about the dynamics of landslides, and then with this knowledge, this may be included in coupled models of landslide and tsunamis in order to get better estimates of tsunami heights. With this, I would like to close my talk. Thank you for your attention, and I'm open to questions.